Hello guys, today I'll be taking you through the tutorial of induction motor, tutorial 3 of electrical machines. So in this board, what I've drawn, I have drawn the power flow diagram, which is the power flow of an induction motor. So before we get into any calculations, I'd like to explain just what is happening here a little bit before we go and calculate. So as you can see, this is our power flow diagram. Here we have our P-in, which suffers the two losses, which is a stator iron loss and the stator copper loss. Now, the formula for a stator copper loss, it is given by PSCU, that is equal to I squared R. This is how we determine the stator copper loss. Now, the power that moves from P-in to a rotor, it suffers these two losses. It suffers these two losses. In another words, I'm trying to say, if we were to determine the power in the air gap, we're going to say P-in minus P stator of the iron loss. This is the losses due to eddy current and hysteresis, and then minus the stator copper loss. This is equals to P air gap, which is the power that goes through a rotor. So at this point we have the power. P-in is supplied to an induction motor, goes through these losses, and we have the power that goes through a rotor. And the power that goes through a rotor, as I've explained, that it is known as a P air gap, or it can be a P input into a rotor, or it is also known as an electromagnetic power that goes through a rotor I mean. Now in a rotor we have this kind of two losses, which is the rotational copper losses. We also have the iron rotor losses, but these ones, they are so small, so they are considered ignorable. You can always ignorable because they are very, very small losses. So in the rotor we only have this, which is a rotor copper loss, and then from a rotor we have a power. This one is a power developed, which is an output from a rotor. It is a power developed. And before we even reach the output, the total output, it suffers again the rotational losses. Now these are the losses that occurs after we have the output power, which is the P developed. So I would like you guys to take you through some formulas, derived formulas of these stages of powers, whereby we'll be using those formulas to calculate our powers. As I've said here, we have the stator copper loss, which is given by 3I squared R. This is a stator copper loss. Now we have this power, P air gap, or it's P-in to a rotor. It is given by P-in minus these losses, which is the stator iron loss, minus these losses, which is the stator copper losses. P air gap is also given by P RCU, which are the losses of the rotor copper loss divided by a slip. This S is slip. And then it can also be given by PBM divided by 1 over S, which is also a slip. And this formula can be derived anyhow. Even if we, let's say for example, they say calculate PBM is just gonna be PBM is equals to 1 minus S times PAG. That's a straightforward. I hope you understand that one, guys. Yes. Okay. Having explained that, I hope you understand what is happening here. You can get this list of formulas from any textbook. They showing these formulas. I was just explaining few before we go to calculations. Okay, another thing that I have to explain. If you have this system like this and it's given at no load, you must understand that P out at no load is 0, and the rotational copper losses at no load, it's also 0. So what you can do, you can find with stator, these are the stator ion losses, by using your P in and also using your P rods, which are the rotational losses. Most of the time it's always given on the data. And you can also use these ones, which are the stator copper losses given by current and the resistor of a motor. Guys, having said that, this it's whereby you are, in fact, at no load, the purpose is to find out the stator ion losses using the input power, using the rotational losses, and using the stator copper losses. Now at full load, we have found the stator ion losses, which are the same as at no load. P rotational losses, they stay the same. Now we find the P in given in, we have to find the new Pn at full load. Here we have calculated this one at no load. P out, it's what we are looking for. P out is also given. We have to calculate this guy at full load, and this one, it's also given by using the current at full load. So how we're gonna get a P out? Firstly, we're gonna calculate P a gap, which is given by P in minus P S Fe minus PSCU, which are the losses in a stator losses. And then our rotor copper losses are given by the slip times the input power to the rotor. Then we find our P out. Now, as you know that the efficiency of a motor is always P out over P in, we can calculate the efficiency. If it's given in percentage, we'll always multiply this guy by 100%. And also, as I've explained here, that this ppm is given by PAG times 1 minus S, which is a slip. And then the P developed, you can calculate it using okay, before we come here, I want you guys to remember that T developed times omega is equal to P div, where is equals to 2 pi n r. This r is for rotor, guys. So if you were to calculate the P developed, you're gonna have P div is equals to T developed times 2 pi n r. Yes, I hope I try to summarize these formulas, but I hope you understand better when you start doing the solutions. So I'm gonna write the first problem on the board and then you start solving problems. Let me just take 1 minute break. Then, okay, guys, we are back with solving problems. So the first problem that I'm gonna start with, I think it's gonna make you understand better what I was explaining. We are given that a 440 volts 3-phase induction motor takes current of 52 amps at the lagging power factor of 0.8. Okay, this is I full load, and then they said at no load the current is taken 15 amps. It's taken to be 15 amps, and the input power was 19. During the separation test, it was found out that the no-load rotational losses are 500 watts. Now remember guys, I said this losses stays the same whether it's full load or no load. The resistance per phase of the delta connected starter is 0.7 ohms. Calculate the output power and the efficiency when the rotor runs at 0.05 sleep. Now this is the expected answer from these calculations. So here we're gonna have to calculate, we are needed to calculate the output power and the efficiency. This is the expected answer for the efficiency. So I'm just gonna start here by writing my data that I have, which we have V is equals to 440 volts, and then I full load we have 52 amps, and then we have the power factor of 0.88, and then the current I no load is taken to be 15 amps, and the input power, this is the input power at no load, which is P in is 1.9 kilowatts. What else are we given? We are given the losses, which is P rotational losses is equals to 500 watts. The resistance again of a rotor is equals to 0.777 ohm. Sleep is equals to 0.05 per unit. Now guys, let me just write this thing here. Okay, firstly, what we're gonna calculate, we have to calculate the P out. As you know guys, that first of all, P in, it is given by P out plus P losses. And then here, it's P out plus, we name all the losses that we have here, which is P, S, F, E, P, S, C, U, P plus P, R, C, U plus P, rotational. And remember, when we calculate for at no load, remember I said at no load P out is equals to 0, and P RCU, which are the losses in the rotor, they are also equals to 0. So now at this point we are left with P in is equals to P S F E plus P S C U plus P rotational. And remember guys, this one is given, this one is there, this one is there, and I said well, at no load we calculate the iron losses of a stator. So our formula here, this at no load we only determine the value of this guy. We're gonna have PS FE is equals to P in minus PS CU minus P rotational. And then we were given that this guy, it is 1.9 kilo minus, remember I give you the formula for this one, which is 3. And then we have I at no load, the current was given 15, it was 15 amps divided by root 3. The reason for this, they said that if you can remember, at no load the rotational losses, the rotational losses are 500, and the resistance per phase of a delta. The reason why I'm dividing by root 3, it says, they said per phase of a delta, which means we are dealing with the delta here. It's squared times the resistance, which was given as 0.777 minus the rotational losses, and then our answer is expected to be, okay, let me just take my calculator. Okay guys, let me just calculate. Okay, what I get is 1,225.175 watts. Okay, this is the value that you get at no load. So now guys, here I just substituted, assuming that you still remember that our PS, the copper losses of a stator, are given by I into, I squared R. But at this instant, because it's under a delta, is 3I squared. As you can see, that we divided by root 3 right there. Okay, now we're gonna move to calculating our P out now we calculate our P out at full load. At full load. Now, coming from here, P out plus all these losses, they make P in. At full load, we have to calculate P in. We don't know the value of P in. The value of P out stays the same, doesn't change. And the value of PSFE, which are the stator iron loss, they stay the same. We have to calculate PRCU, which are the rotational losses. We don't know them. What else do we have to calculate? Let's see. P out, we have this, we have to calculate the value of copper losses of a stator at full load. So let's just get right to it by first start to calculate P in before we can come back to this formula to substitute. Let us calculate our P in. P in is given by root 3 VLIL cos theta. We have root 3. Now the voltage, it was given as 440 volts. Our current at full load, it was given as 52, and we have our power factor as 0.88. Now what do we have here? What I get is it's 34873.804 watts. This is our value of our P in. Okay guys, after calculating our P in, we have to find our PRCU. Remember the losses in the rotor are given by slip times P gap, or PR input into a rotor. Now we have to calculate our P air gap, which we don't have currently, but it's also given by, you remember when I was explaining it in the flow diagram, it's given by P air gap is equals to P in minus PSFE minus PSCU. These are the iron losses of a stator, these are the copper losses of a stator. Now at this moment, as we have calculated our P in, it was given as 34873.804, and then I have said, this one at no load or at full load, it stays the same. So we calculated it at no load and it was 1,225.175, and our PSU now at full load, which is 3. Remember our current at full load, it was given as 52, so we have 52 divided by root 3 squared times 0.777, and then our expected answer, it's gonna be, let me just calculate. It's 31,547.621 watts. Now we can find the value of our PRCU, which is given by SP gap. Our slip, it was given as 0.05 times 31,547.621. And then what we have here, I got 1577.381 watts. Now coming back to our formula here, we have these losses, we have these losses, we have calculated these losses, we have calculated these ones. This one in fact it was given. So now at this point we can calculate our output power, which is gonna be P out is equals to P in minus the losses, which is going to be P S F E minus P S C U. This one is at full load minus P R C U minus P rotational. So to just make things more simpler here, let's just calculate this guy, this side, which is going to be PSCU. It is equals to 3 into 52 root 3 squared times 0.777. And it's given as 2101.008 in watts. So we're just going to substitute our values that we have found in this to get the output power. The first value was 34 for P in 34,873.804 minus the value of the losses of a state of the ion. It was I mean like ion losses of a stator, 122.5.175 minus the copper losses of a stator at full load, 2101.008 minus the losses of a rotor is 1577.318 minus the rotational losses, which were given as 500. So what do we have here? If I punch my calculator very well, it's giving me 29,470.303, which is in watts. Now to calculate the efficiency of this guy, it's gonna be, as you know, our formula for efficiency. Efficiency, it's P out divided by Q, which is equals to 29,470.303 divided by our input power, which is 34,873.804. What is the answer here? 29,470.303. Our answer it is 0.845, which is per unit. But if you want to make it in percentage as they wanted it there, you just multiply this guy. You just multiply this guy by 100, which is gonna give you 84.5%, which is the same answer that was expected here. So I hope you guys learned something from this video. If there's something you didn't understand, remember that you can always get our notes and you can always ask our questions. So let me just take 1 minute break and I'm coming back with another solution of a problem. Okay guys, second problem, we are given that a 3-phase 2-pole induction motor has a starter connected rotor with the standstill impedance given as 0.1, where J it is 0.4. This is our reactance per phase. The voltage between the slip ring is 218 volts at standstill. So now I'm gonna just start by giving my data here. Given data, our V phase it is 218 volts. Okay, and then calculate the value of the impedance in series to limit the starting current to this one. So they want our Z in series, which is unknown. What do we have here? We are given our ZR, which is 0.1 plus J 0.4. Now they want our Z series. Okay guys, to calculate our Z series, we have to know the value of our Z total. As you know that Z total is equals to ZS plus ZR. So here, what is it that we have, guys? I assume you guys, you are familiar with this formula that says IR, it is equals to IO divided by the resistance of a rotor plus of a rotor. And then in this case, we are looking to calculate our Z total, whereby we are given the current of a rotor to limit the starting current. Okay, so basically here we're gonna calculate this guy, which is the impedance. And guys, remember that our voltage, our VP is given as 218 volts per phase. So if we need it in per line, V per line is gonna be VP divided by √3. So yeah, let's just get to it. We need to calculate this guy, but we must find the value of this guy, which is gonna be ZT is equals to IO divided by √3 IR. And then we have the value of this IO, which is 218 divided by the √3 into our current. It was given here as 85 amps. Calculate the impedance in series with the rotor when you are given the starting current at 85 minus 35 degrees. And then our answer is 33 times 35. That is 1.213 plus J 0.4. 849 ohms. This is our Z total, and then to find the Z series is going to be Z total minus Z series, which is going to be 1.213 plus J 0.849 minus 0.1 plus 0.4, which is given in the data. And our Z series is going to be 849 Remember this, guys, this one is an imaginary number. So our answer is 1.113 plus J 0.449 ohms. This is our value. This is the impedance that is needed to be connected in series to limit our current. Okay, this is it was our first question, which was number 1, question A. Moving on to question B, at what slip will the maximum torque? Okay, so the formula for this guy, it's X maximum is equals to R over XL. Now this one is of a rotor, guys, always remember this one. So we are given that the resistance of a rotor is 0.1 and the reactance it is 0.4. So at what slip will the maximum torque occur? It's going to be 0.1, 0.4. It's going to occur at 0.25. That is for our second question. Coming to our third question, what will be the maximum frequency at this torque? So now calculating the maximum frequency of this torque. In South Africa, guys, we are using the standard frequency, which is 50 Hz. So a maximum frequency at this torque, F maximum, is just gonna be the slip times the standard frequency, which is 50 Hz. So it's gonna be 0.25 times 50, which is gonna be 12.5 Hz. Okay, thank you so much, guys, for watching this video. I hope you benefit something. For more videos, please subscribe to our channel. Thank you so much.